and we have the two boundaries of the slits already defined, already fixed in space. But the coordinates, we don't quite fix the coordinates. And this is a good question to ask why. That is because when we establish this model, remember what I'm doing, what I'm saying? When you want to look at this intensity, you define your origin here. When you want to look at the intensity here, then you define your origin here. And that is because at the very beginning, when we develop the theory, we set one condition. The condition is that we need to have no more instance. Okay, we need to have no more instance. If you don't change your coordinates, this assumption fails. For example, if I look at the intensity here, when you want to look at the intensity here, then you have an angle. So this assumption fails. So you have to shift your coordinates at the same time if you want to look at your intensity here. Okay, you got it, right? Because we have a very strong assumption here that we're going to have no more instance. And then, based on this, we come up with these results. So whenever you want to figure out the intensity at this location, you redefine your origin relative to this aperture boundary. And then once you redefine your origin, then your W1, W2 also change. That is why. Okay, so this is something that I want to tell you. Now, let me continue this Fourier zone discussion. I don't believe I can finish all the materials in my handout in this semester, but at least I want to give you a very clear physics for whatever I talk about. And I think I'm going to finish the Gaussian laser beam materials, and then perhaps some Fourier optics, but then the coherence of light will be removed from this semester's lecture, and that is more advanced anyway. Okay. All right. So now, if we have an aperture A, then at location L, then you can have the Fourier, a different Fourier radius, the radius of the successive zones. At this location, at this calculation, we still keep L is a constant. Okay, but then in fact we can allow L to be a variable. Okay, given a Fourier zone, given the aperture radius, just keep this aperture to be a constant. For example, I have the laser coming out from this aperture. Okay, so this aperture area is a constant, and then you allow this L to be a variable, and then for different L, you're going to have different Fourier zones. Okay, and with different Fourier zone, you'll be seeing the constructed interference or destructive interference. So imagine that you just walk along this direction and look into this aperture. Of course, you don't want to look into the laser beam, okay? But imagine that you have light coming out from this aperture, and then you look straight into this direction, and then you walk. Then you're going to see that the Fourier zone is going to reduce when you walk along this direction, okay? Previously, at this location, I could be seeing 3 Fourier zones. For 3 Fourier zones, I will have the first 2 zones give you destructive interference. The third zone will have all the light coming into your eyes. But then if I walk in this direction, the 3 zones will be reduced to 2 zones. And then you have destructive interference. If you have 2 Fourier zones, like this, if you have 2 Fourier zones, these 2 zones will give you destructive interference. You'll see a dark point right here. Okay, if I take out this. And then if I walk along this direction again to see 3 zones, these 2 zones will give you destructive interference. and then the light coming out from this zone will be focused to this point. And then you'll see a bright spot. Okay, so if you continue to walk along this direction, you're going to see bright, dark, bright, dark, bright, dark in the near zone. Okay, but in the far zone, you'll be seeing this. In the far zone, you'll see the center part is going to be a bright spot. Always, this is a far zone, far field diffraction, far Hall diffraction. In the far field, the center lobe is always bright. But when you walk along this direction, the story change. You see dark, bright at the center. Wow, that's interesting. But I cannot see. I don't think I can do it here because it's too close. In fact, I sort of see it. Let me see if I can see it, and then I'll show you. No, it's not obvious. It's too close. But if you do the experiment, let me finish this project, and then I will show you one photo that I took before. Okay, all right. So if you just walk along the distance, then you'll see this at the center. Occasionally you have dark spots, and then it turns bright, and then it turns dark again. You just walk along the longitudinal direction. Okay, that is because you have different number of zones in the aperture. Okay, and one definition for a lens is that if I have a bright spot at the center, then you say that hey, this distance is a focal length. So in fact, you can calculate a focal length correspond to a bright spot at the center. Okay, so this is sort of based on some definition of a focal length. Whenever you see a bright spot at the center, the corresponding distance is called a focal length for a Fresnel lens. So this is the Fresnel zone kind of phenomenon. And I told you I want to show you a photo I took a long time ago by using a green laser pointer. And this is the photo I took a long time ago. Sorry for the Chinese character on these slides, but so indeed, you can observe it experimentally. So you see a dark spot at the center. This is a near field diffraction. It's not stable, I don't know why. Occasionally you see this bright spot at the center, but at a certain location, indeed, you can observe a dark spot right in the center. It's fun to see this when you do the experiments. Imagine that, well, you always have the bright spot at the center for this kind of far field diffraction, right? Again, I've been playing this for too long. You always have a bright spot at the center. You wouldn't expect to have dark fringe at the center, but for Fresnel diffraction, you can see this dark fringe right at the center. It's just fun to see this. All right, so this is all about the diffraction, Fraunhofer diffraction, Fresnel diffraction, and the key concept is the phase turn. Whenever you have constructed interference, you see a bright spot. Whenever you have the destructive interference, you see a dark spot. So that is the bottom line for this diffraction theory. All right. Well, I know that for Fresnel diffraction, especially for the cone spiral, it takes a little bit effort and imagination to get everything understood for you. So you need to spend some effort by yourself. Okay, let's study a little bit. All right. Now I want to talk about this laser beam. apparently this is not plane wave, this is not spherical wave. But then we need to understand it because we deal with this all the time. So we'll talk about Gaussian laser beam. And the handout try to extend the discussion of the Gaussian laser beam from the Fourier diffraction. And it's not very straightforward, but I try a little bit. But then eventually I need to involve the paraxial Helmholtz equation. So let's continue the Fourier diffraction a little bit, and then hopefully that we can start to see some formulas which will make sense to you. Okay. All right. So this is the Kirchhoff-Helmholtz integral at this point P, but we already simplified it. Okay. The simplification is that we have forward scattering. Okay. So basically with forward scattering, this term gives you -1 because the origin is right here. So for forward scattering, the source from this origin's point of view has a vector along this direction. Remember that, right? For forward scattering. So this term gives you -1 because n dot rho is equal to pi. Okay. So with n dot rho equal to pi, then this becomes a -1, give you +1 here. And also when we talk about Fourier diffraction, we sort of draw a straight line from S to P, and then make this the angle equal to 0 for normal instance. Okay, so n dot r is almost 0. So you have a factor 2 right here. Okay. So this is the equation we had before. All right, let's continue to make assumption that n dot r is a very small angle right here. So we write alpha. Previously we wrote this as delta. Okay, and then we define the aperture is important. Well, the aperture now we talk about aperture like this, but in fact, for Gaussian laser beam, the aperture is soft. Okay, there's a finite beam size, and in fact, there's no hard aperture associated with it. It's just a field distribution over this. Okay, it's a field distribution over the transverse direction. So we write down the field distribution right here. Okay, so this is sort of stretching the Fourier diffraction and try to construct the Gaussian laser beam that we see every day from this laser pointer. Right, so let's continue to set alpha equal to 0 to be a normal instance. So this is exactly the Fourier diffraction theory. We set this to be a normal instance and take out this alpha. So you end up having this approximation right here. We call this paraxial approximation. And then we do the expansion for the phase term. So you have quadratic term and also linear term in the expression, right? So we have gone through this before when we talk about Fourier diffraction. Okay, so this is sort of understood to you from Fourier diffraction already. All right, so so this is the Fourier diffraction, except that for Fourier diffraction, we define the coordinate system to take out the linear term and keep the quadratic term. Okay. All right. So assume that there's a field for this laser beam is defined like this. There's a propagation term and also a transverse field profile. Of course, for Gaussian beam, well, when you compare a Gaussian laser beam with a plane wave, the major difference is that you have a finite cross-sectional area, right? A laser beam like this, there's a finite cross-section area, so you write it with a finite cross-section area like this. Okay, so we'll be looking for a solution like this. There's a propagation along z direction, and then there's a finite cross-section area. And so from the Fourier diffraction, you expect this finite cross-section area, finite this xy dependence to be like this. Okay, this comes from the expansion of this. Okay, expansion of this. So you'll be expecting some phase, projective phase like this. Okay, and R is the quite far distance, much. This is transverse dimension. Well, this transverse dimension is this big, about millimeter or centimeter. But R, how big is R? Well, R is really big. So you can do some approximation. Take out all the high order terms from the tidal expansion of this, because R is really big. So just keep the first order terms. So you end up having this projective phase. And you have this before for Fourier diffraction. All right. So you have a phase term given by this expression. And all the high order terms are removed. But then, if you just use this as a solution, you find yourself in trouble. Why? Because if you take the intensity, this phase term gives you 1. Okay, if you take the intensity, of this xy dependence is field. So you run into some difficulty. Okay, if you do E xy, you'll be doing the this xy dependence is in the phase term. Xy dependence is also in the x term. Well, this is R only. And so you get 1. This is not a function of xy. Then you run into some difficulty. So this is not a solution for the Gaussian laser beam. But this is the solution from Fourier diffraction. Fourier diffraction is a solution from Helmholtz equation. So this is a valid solution, but it's impractical. So now all the solutions from the Helmholtz equation match to the real situation. Okay, so we need to modify this solution. Okay, we need to modify this solution. Well, the good thing is that the reason that you get this equal to 1 is because it's a complex exponential. It's a complex exponential. But if you introduce this R to be a complex number, if we change this R to be a complex number, A plus JB, the story is different. Well, R is just a constant in this calculation, right? It's a distance between along the longitudinal direction. And so R, if I multiply R to be a complex number, then this calculation is going to give you exponential, something like x squared plus y squared divided by b, something like that, minus. It's going to give you a Gaussian cross-section. Okay, do a calculation by yourself. And if you change R to be like this, it is still a solution of the Helmholtz equation. Okay, so now we understand that we just need to do this transformation to get the right formula for describing the Gaussian laser beam. Okay, so this is the, well, the goal is to have this. The goal is to have this. Because in real case, you have a finite cross-section area for the laser beam. Okay, so the key is that you need to change this R. Okay, you need to change this R to define a new radial curvature that is complex number. Okay, we define this R to be a complex number consisting of the real part and imaginary part, and then you will end up having these results. And with this change, it is still a solution of the Helmholtz equation. All right. So this is the key to make a transition from Fourier diffraction to a Gaussian laser beam by defining a complex radial curvature. Okay, with this transformation, you end up having this intensity dependence along the transverse direction, and this will properly describe this Gaussian laser beam. Okay, and now W has a physical meaning associated with it. W basically is the radius. It's 1 over E. This is the W here. This will be along x squared plus y squared direction. W, if this is 1, this will be 1 over E, E0. So this W has a physical meaning associated with it. It's the radius of the Gaussian laser beam at 1 over E of the maximum electric field location. All right. So this is sort of a stretch from Fourier diffraction to a Gaussian laser beam. But later I'm going to give you a different approach to derive it. Okay. But this is given in your handout. All right. So we have one formula to describe a Gaussian laser beam based on this transformation. The geometric radial curvature is changed to a complex radial curvature, and this, in fact, is the accounts for the diffraction of the beam due to wavelengths. For this 1 over R is a spherical wave. Okay, it's a spherical wave radial curvature, nothing to do with diffraction. But with this term, you have the diffraction due to the wavelengths. Okay. All right. So now you have a Gaussian spherical wave given by this and complex radial curvature to start with from this location. Okay, you have this. You put this into the Fourier diffraction formula to start with. Then you start to propagate the wave along z direction. Remember, the theory is like this. You have something to start with, and then you have the wave propagate downward. And then we try to understand what that is. Okay, so put the Gaussian spherical wave into this location and see what happens. And so let's do an integration. If you do an integration, you found that the result is like this. Again, now your radial curvature is a function of distance. And then you have additional phase coming out. And then in front of it, the spot size will grow with distance. Okay, and once you finish this Fourier integral, and you end up having your complex radial curvature grow with distance from an initial value. Okay, and don't forget that your initial value is right here. So you have initial radius. You have initial radius. But then once you propagate, this Q will grow with distance. So this is how we obtain from this linear diffraction theory. All right, and then the rest is how we use it. How we use it. Okay, so this is a theoretical basis for you to go forward, but the rest is how we use it. So if we put this again, this transformation, if we put this transformation into this formula again, then you end up having this somewhat complicated electric field for Gaussian laser beam. And this plot is responsible for the finite transverse cross-sectional area. And it's a Gaussian function, given a beam radius of this W, but it's a function of Z because the field starts to propagate over Z distance. And then this is the like a plane wave-like phase going along Z direction, and along the transverse direction you have like a split wave-like radial curvature. Okay, away from in addition to this plane wave phase, you have some sort of split wave phase along the transverse direction, and then there's an additional mysterious phase. We call this Goyo phase. Okay, so this is the whole thing, and then if we just copy it down here, and write down the specific expressions, it's most convenient that we define a parameter called optical real range. Okay, so this is the definition. Because we want to simplify the discussion, then we define this the optical real range. And turn out that once you have this definition, the formula becomes much easier to write. Okay, so define this optical real range. That is pi, the width radius squared divided by the wavelength to be an optical real range. And then write everything in terms of optical real range, then the formula becomes easy. Otherwise, it will be very tedious. Okay, so this is the just try to sort of simplify the discussion. So we define this optical real range, and then everything can be discussed based on this optical real range to understand how this radial curvature will change, how the beam radius will change over distance, and so on. Okay, for example, the geometric radius of distance, a radial curvature R as a function of Z, now can be written into the Z plus square of optical real range divided by Z. So when Z becomes very, very big, this term goes away. It's just a sprig wave. Okay, for Gaussian beam, when this Gaussian beam propagates to the moon, for example, the beam size is going to be huge. So it's just a sprig wave. So this term disappears. Okay, it makes sense to you, right? You can, when you have a very long distance propagation, this term goes away. All right, but in the near field, the story is different. Okay, this is going to play a role in the near field because when this Z is equal to 0, what happens? Wow, this becomes infinite. What does it mean? For Gaussian laser beam at Z equal to 0, at the reverse location, you have plane wave-like solution. So the wavefront, if I show you the wavefront right here, if I show you the wavefront right at the center, this is the wavefront. When this wave propagates to a long distance, then this is going to appear to be like a sprig wave or plane wave. But then at the center, you also have plane wave like a wavefront right at the center. So this is what it means. So this is a Gaussian laser beam. Okay. So at this location, the plane wave solution is still valid. I need to go back. All right. And for the beam radius, well, this term gives you the beam radius. The beam radius is like WZ, which is 1 over E field point. Okay, this beam radius is 1 over E field point. And this W as a function Z is given by this expression. That is the width radius. For Gaussian laser beam, this is where you have width radius. And then after this, the focal point is going to expand. Okay, the expansion is based on this ratio Z over ZR. Starting from this W0, when Z equal to 0, this location, Z equal to 0, you have a width radius of W0. Okay, and then you start to grow. And then the mysterious phase is Goyer phase, given by this octangent expression. Okay, from the theory. Okay, so this is a stretch from the Fourier diffraction. Well, another way to solve this problem is that just looking into this, the Helmholtz equation. Okay, and try to find a solution satisfying this. But then for this laser beam, the beam spot size grows slowly compared with this oscillation. Agree? Well, this oscillation will have, for this laser light, red light, this is about 600 nanometer. But this distance is a few meters. The difference is 6 order magnitude. 1,000,000 times difference. So this envelope has a length of meters, and this is like 600 nanometer. So apparently this envelope grows very, very slowly. Okay. So in this calculation, this slope, the slope of this envelope is like this. The envelope field divided by the change of distance. And then this oscillation has a change of the envelope field divided by the wavelength. Apparently this is much, much larger than this. Agree? Shukai, you can see it, right? This is much, much larger than this. Because this is 600 nanometer, this is on the order of perhaps meters. All right, so I can simplify this calculation based on this. The simplification is going to give you, well, so I can just adopt this to have this approximation, and then do a second, well, based on the assumption, then you get this, the so-called paraxial Helmholtz equation. Okay. So previously you have Helmholtz equation, and that is difficult to solve. But now, if you agree that the Gaussian laser beam satisfies this condition, then you start with this paraxial Helmholtz equation. And then for this paraxial Helmholtz equation, you can figure out a solution like this. And in fact, this is just the Gaussian laser beam. Okay, but this is a fundamental mode. Later we're going to talk about higher order modes. Okay, so this is the Gaussian laser beam. And this expression, this Q is equal to Q plus GR, so the ZR is the optical ray range. Okay, it's some coefficient, okay. We don't know yet what this is, but later you're going to see that once you put this into expression, then you expand it, then you get the, you understand that this is the definition we had before. But then I want to echo this result with the previous discussion. If you, let's go back to this discussion, and we found that, hey, this is the result from the Fourier diffraction, but then we have the intensity equal to 1. That is not good. So we make a transformation by taking this radial curvature to be a complex number. Right? We did this transformation to get the Gaussian laser beam. And you see that, hey, this is in fact what we are doing right here. See, this is radial curvature. We change this to a complex number. Okay, we change this to be a complex number to get the Gaussian laser beam. The same thing. Except that if you put this into paraxial Helmholtz equation, you can verify that this is a solution you want. And this rho is x squared plus y squared. So it's better that I write like this. So it's not confused with you. This one. So this will be consistent with what we discussed before. All right, so this is the valid solution to the Helmholtz equation, even though we make some approximation. All right, so if I just spell out, okay, just expand it, okay. Now you have Q equal to Z plus ZR, and then expand it. You get this with the definition of W and R. Okay, so this is just an expansion from the previous expression. Because when we write down this, in fact, we don't know what this is. It's not transparent in physics. Because this is complex number, and then you ask, what the hell is this? Well, expand it. You expand it, and then you start to define this R and W, and then everything makes sense to you. Because you know that this R is the geometric radial curvature, and then you know this W is the radius of the beam as a function of distance, and then this will grow with Z. Well, how do I know it will grow with Z? Well, I plot this by myself. Okay, you see that at Z equal to 0, you have very high intensity at the center, and then once you walk along the Z direction, one optical range, the intensity drop, but the radius, the size become bigger. It makes sense to you. And then if you walk to the plus minus 2 ZR, then the intensity continues to drop. The beam size becomes bigger because of diffraction. So this is Gaussian laser beam that we are using right now. Yeah. So this makes sense to you. So the beam radius is given by this, described by this the optical range, and then we have additional the beam radius, width radius defined at the Z equal to 0. When Z equal to 0, you have this the width radius given by relevant to this optical range. Okay. And then you have the wavefront radius, or this is geometric radial curvature given by this expression, and you have Goyer phase. Yeah. So this is sort of the Gaussian laser beam theory we obtain either from the Fourier diffraction or from the paraxial Helmholtz equation. Okay. But then, once you expand it like this, you start to understand the physical meaning of every variables. For example, when you look into this W, you know that this is the radius. This is give you the finite cross-sectional area of the beam. Okay. So this is Gaussian laser beam, and for the optical range is given by this expression relevant to the width radius. All right. And don't forget that the propagation rule for the complex radial curvature is like this. It's the grow with Z, starting at z equal to 0, it starts from the optical range. And then you have this inverse law to relate the radial curvature and also the spot size when you start to propagate. Okay, so take the inverse of this. You organize it into this form. All right, so this is the sort of complete theory for the fundamental Gaussian laser mode. And this is not the only solution from the Helmholtz equation. Okay, there are higher order modes we'll be talking about on this Wednesday. But you more or less understand that for Gaussian laser beam, we now have a theory to describe it. All right. After 2 hours, most of us are exhausted. I hope that at least you catch the concept. And I will see you again online on this Wednesday.